So I've recorded 10,000 hours of driving data. Now what? This is one of the fundamental questions that face automotive companies that are developing autonomous vehicles today. Before I answer that question, short introduction about my company and what it's about. I work for a Berlin-based startup called Merantix. Merantix is a venture studio, which means that unlike normal companies that build products, it actually builds companies. And it has already built 3 different companies. One is Merantix Healthcare that does automated screening of breast cancer images. The second is Merantix Labs that does consultancy for machine learning and AI. And then Merantix Automotive, of which I am a part of, that develops the product SIA Search, which I will talk about here today. Now, what is the problem and what is SIA Search? Going to give you a brief overview. So the amount of data for autonomous vehicle today, for researchers that are developing them, is exploding. A single autonomous vehicle creates up to 10 terabytes of data per hour, which is about 3 gigabytes per second, or the equivalent of like 100 average smartphones per hour worth of data. With all this data, it's really hard to find the information you need. The engineers that are building these vehicles, they need some very specific data, and when you have this sea of data, it's really hard to figure out actually what's in there. On top of it, it is expensive, because if you want to know something about data, what's in there, what's happening, is there something interesting going on, you need manual labor. You need people in the cars annotating, oh, here's a lane change, oh, here are some pedestrians, here's something interesting happening, or people just watching videos on screen and figuring out what was actually happening. And on top of that, infrastructure costs, such as cloud computing and cloud storage, explode quite rapidly. Now, the fact that this is done manually, the data is found and accessed manually, means that majority of the data that is collected remains unused. So even you can only look at a fraction of the data you actually collect. Our solution is this pipeline you see above me. First, on the left, you take the raw data from the vehicles, you feed it through some sort of a data processing that adds additional layers of data on top of the raw data. Things like, oh, how many pedestrians are there? What's the weather like? You know, is there a lot of traffic in the scene? This additional layer of data is then fed to a database that can be accessed via a user interface or some sort of an API to find the exact data that the engineers developing these cars need. Now, a little introduction about autonomous driving and autonomous driving data. As you all have probably seen in the past few years, there are great promises about autonomous vehicles, which basically means, summarized in this great stock photo, this incredibly handsome, overly well-dressed man can just sit down, relax, and read a book on his way to work or wherever he is going. Now, autonomous driving is not a binary thing. There are defined multiple levels of autonomous driving. Level 0 being no automation, just a human driving the car. Level 1 is some sort of a driver assistance, like the cruise control in your typical car. Level 2 and 3 are kind of hard to define, but you can just think about the current state of the Tesla autopilot. Level 4, that no one has reached yet, is high automation, which means you have a fully autonomous vehicles that can drive in certain sections, but then it hits a gravel road and says to the user, sorry, I cannot do this, please take over. And finally, there's level 5, full automation, a car that can drive you anywhere, and it's a car without a steering wheel, basically. And these research vehicles that are used to develop autonomous vehicles today, an autonomous vehicle system, looks something like this. Just want to draw your attention to all the sensors on top, which is kind of the focus of our product, the data produced by these sensors. These sensors of camera, LiDAR, GPS, radar, and IMU, and the most typical setups. There are, of course, differing setups depending on which companies are doing it, but these are the basic ones, and I want to tell you a little bit about them. So, camera, we all know. This is quite a modest setup with only 6 cameras, such that the car can see 360 degrees around it. There are lidars that basically shoot light all around the car that allows the car to build up a 3-dimensional representation of what's going on in the scene. How far are the other cars? Where are the pedestrians? How far away is everything in the actual scene? And that can build up images like this. There's the GPS, which I guess all of us know. Where are we located in a map? And on top of that, a lot of vehicles are equipped with radar that have a similar purpose as a LiDAR, but different strengths and weaknesses. And then the IMU, which basically tells the car how it's moving through space. Now, all of these data, they take up a lot of space. And just to illustrate how much space it is, this is like a back of the envelope calculations for the amounts of data for a single car. Let's say we collect the data for 1 year. We want to store that data for an additional year. The cost I put up here is like a typical cold line glacier storage cost from Amazon or Google Cloud Storage, basically the cheapest thing you can get. So it produces, as I said before, 3 gigabytes of data per second. It runs 3 hours a day, which is 30 terabytes. It runs for 310 days a year, which gives you 10 petabytes of data for a single car. Multiplying that all together, the data the amount of money you need to store data for a single car is on the order of $500,000 per year. This is just storing the data on the cloud. This is not the cost of the hard drives, moving stuff around, logistics, or anything like that. So it's obviously impossible to store all the collected data, especially when you have a fleet of cars. And even if you could store all the data, you can only access a part of it, because there are humans that are actually labeling it and imbuing it with some added data that allows you to search through it. And currently, rather than look at the 95% of the data they already have to find what they need, because it's too difficult to look through it, the developers of autonomous vehicles usually just send out 10 cars. Hey, we need crowded junctions. Please send 10 cars, collect the data, and bring it back, instead of looking through the data that they already have. So you can't store all the data, and you don't want to store all the data, because most of the data is not really interesting. What is interesting is some sort of interesting or some sort of anomalies or difficult scenarios. Those could be crowded junctions, construction sites, or unexpected behaviors of other agents in the scene, which is other pedestrians, bicycles, cars, etc. This is the data you want to store. And what do you use this data for? You can use it to train machine learning algorithms, the ones that are used to see the environment around the car. How does a car detect objects? It uses a computer vision neural network. You can use this data to train it. You want to evaluate some systems on the car. Maybe you have an automated brake system that you want to try out, and then you need some data of challenging situation. Or you simply want to do, as an AV engineer, autonomous vehicle engineer, you want to do some data exploration. How does a car behave in Paris as opposed to Berlin, for example? Now, our solution to this data problem for the autonomous, for the car companies is SIA Search. This is basically the same image I showed you before, but in a slightly different format. You have the vehicle data on the left, the cameras, the LiDARs, the GPS. You feed them through some data processing that adds something interesting, some metrics on top, some added layer of data that you can then use. And in this case, this added information has been categorized depending on criticality of the data. So very critical data is something like a crowded junction, and not so critical data is empty highways. You store this additional layer of data in a database that the engineers can then access to figure out what's going on. So just some examples of these metrics that you might want to add on top of your raw data. There's some basic stuff like how fast is the car driving? There's maneuvers, is it changing lanes? Maybe you're developing an auto honking system that you want to honk every time someone cuts you off in traffic. Then you need to detect cut-ins of other vehicles. You want to see the speed limits, where is it located, et cetera, et cetera. And these are only a few examples of what you can add on top. Now, what does this look like, actually? So here are some example searches that an engineer at these companies might do. Let's say I want to find something that has the traffic sign yield, which is bilskilta for the Icelandic people in here. It's in an urban area, it has multiple lanes. I want there to be a right turn in there, and I want the car to be changing lanes. What does this look like? Well, you could get something that looks like this. The car is driving, it fulfills all these criteria, but even though you only asked for these 3 things, there are many other things that are happening, many other data that are on top of it. There's the lighting, there are bright and shadows, what's the weather like, is there a construction site there? And then there are many other pieces of information that you can also get from this. Another search, I want something where pedestrians are crossing, I want the max speed to be 30 kilometers per hour, and I want it to be located in the beautiful German city of Karlsruhe. You might get something like this. And as you can see, this is an incredibly challenging scenario. There are very narrow roads, a lot of pedestrians, there's a lot happening, and if you're developing autonomous vehicles, you want to validate them on data like this. And as in the previous one, we have many other things that are going on. What's the road category? How much is happening in the scene? What are the environmental dynamics like? They're obviously high, there's a lot going on here. Now, just to get a little bit more technical, I want to use the rest of the talk to explain how you might develop one of these extractors, one of these metrics that gives you the information that you put on top of the raw data. And for that purpose, I'm going to talk about a lane change detector. Now, why would we want to, so that everyone is on the same page. This is what a lane change looks like. I guess you might have known that before I showed you the video, but let's leave it at that. Why is a lane change important? Why do we want to do this automatically? Well, first of all, there's a lot of manual labor involved in marking these things. So either a person is sitting down, marking videos, or there's an engineer in the car pressing his iPad every time you change a lane, which doesn't scale, obviously. And lane changes are interesting scenarios, they are difficult to perform, and there's a lot of things you need to know about your surroundings when you are doing a lane change. So autonomous vehicles need to be good at lane changes. So let's go for the first approach that you might take if you want to develop a lane change detector. First, let's look at the trajectories of the car. That's the GPS and the IMU. It tells you how the car moves through space. Now, if the car is driving straight, then it swerves a bit, and then it continues driving straight. It must be a lane change, right? This is conceptually simple. It's easy to implement. Should work. But everything has a corner case, especially simple methods like these. And here on this very strangely shaped road, you can see a curved road, and the path that the car takes is actually exactly the same as if it was changing a lane in a straight road. So there is no way of differentiating the two from this method. This is, of course, kind of a simplified example, but it's there to highlight that there are always corner cases that you can't foresee or you don't think of when you start developing things. Okay, let's give up on this first approach. It's too simplistic, it's too hard to generalize. Let's go for the magic, the big guns, the AI, the main AI thing, neural networks. Let's just take a bunch of data, let's feed it through a neural network and train it. And just if you've been living under a rock for the past 7 years, neural networks are the main thing that the AI hype has been about for the past, 6, 7 years. And if you listen to people like Elon Musk, these are the things that are going to take over the world in few years. So, neural networks, they are the state of the art. If you get them to work, they are the best thing you can get for vision problems, but they also have a lot of drawbacks from an engineering perspective. And I want to talk a little bit about the drawbacks for this specific use case of a lane change detector. Now, first of all, they are tricky to train end to end. And what do I mean by training when I talk about neural networks? Well, the way they learn about the world or about vision problems is that you have labeled data, images of cats and dogs. Each image has a label. This is a cat, this is a dog. You feed it through them, and that's how they learn what a cat looks like and what a dog looks like. That's called training a neural network, having it learn about these things. And this is a very difficult process. It's tricky to get right. And people often talk about the 5 stages of training a neural network. There is, let's see. This is quite a cliffhanger. This thing stopped working, so let's move on to the next one. Yeah, people often talk about the 5 stages of training a neural network. All right, this doesn't work either. Oh, there you go. Ah, okay. All right. Spoiled my... all right, there is the 5 stages: denial, that something doesn't work. There's anger, bargaining, depression. And finally, the acceptance that something didn't work, and then you try something new. Just for context, when you look at the image on the right, of course, it doesn't really tell you anything about what's happening, but these lines are something you spend a lot of time looking at when you're training these networks. They're not supposed to be squiggly. They're supposed to go down, and they're all supposed to be similar. So this is obviously quite a tricky problem, which I, in this case, didn't manage to solve. But apart from that, there are other things that are tricky about it. There's a lot of knobs to tune. There are a lot of numbers that you need to tune to get them to work. The bugs you get are infuriating. There's like no way of figuring out what exactly is happening. You just have to try and try again. They have long iteration cycles. So if you want to try something, it might take a day to train it. So you try something, you wait a day, you see it didn't work, then you try it again. Then you always have to wait 1 day to figure out what actually went wrong. They might learn the wrong thing. So maybe if the lane change always happens around the Brandenburg Gate, it might just predict that, you know, if you see the Brandenburg Gate, just give it a lane change. And evaluation is also difficult. So they are also challenging to generalize. And what do I mean by challenging to generalize? Here you can see 2 different photos. One of them has a lot of green boxes. They both have a lot of green boxes and red boxes. The green boxes are basically something a human put in there, the ground truth, the actual thing that is happening in the image. Where is a car? Where is a pedestrian? And the red boxes are where a neural network predicted that there is something there. So is there a car there? Is there a pedestrian? Something else. Now, what a lot of people don't know is that if you train a neural network on data that looks a certain way, so in this example, the neural network was trained on data that looks like the image below, and then you try it out on a different image. And this different image has a different shape. You know, the roads look different, the houses look different, the cars look different. It's not going to perform very well. This is actually kind of surprising given all the hype around neural networks. And even just taking a camera, moving it, you know, a meter to the right on your car, then you would have to do this whole process again because the performance of the neural network will actually degrade. Also, the computations of a neural network are very time-consuming. They take a lot of time to process images compared to a lot of other methods. And therefore, you have to be very careful if you're processing a lot of data, especially a lot of image data, that you have to take care that you have the computational budget to actually feed things through. But if you can get all these things working, you should definitely use neural networks. If you can generalize or you don't need to generalize, if you can afford the time-consuming computation, you should do it. But for us, developing this lane change detector, it didn't work. It was just too heavy, it was too difficult, so we went with a different approach. This is the third approach. This is very simple. You take the raw data and you say, all right, if the lane marking in the middle moves from one place to another, that's a lane change. So we just crop the image right in front of the vehicle. We find all the lines in the image that should correspond to lane markings, and then we feed it into a Markov model. I don't want to talk about what a Markov model is, but it basically takes care of the time component, because a lane change happens through time. It starts at one point and it ends at one point, and that's what the Markov model does for us. This didn't work out as well as we would hope, because there are a lot of other lines in roads except other than these lane markings in the middle. So what we did, well, we added a neural network in there, but it has some caveats. So this thing does exactly this. This is exactly the same, except that you have a neural network that classifies if there is a lane marking in the image or not. If there is a lane marking, we find it using our line detector, and we feed it into this Markov model that handles the time component. If there's not, we just skip it. And now I spend a lot of time, telling you about the limitation and difficulties from an engineering perspective of using a neural network. Why do I have one here? Well, in this case, it's not the whole pipeline, which means that it's a simpler problem. It only needs to look at a small image, which makes it much faster. The fact that an image only looks at the road means that it's much easier to generalize. Because, this section of road in front of a car looks relatively the same everywhere in the world, and it doesn't need, it needs some labels of what a lane marking looks like and what it does not look like, but it doesn't need nearly as much data. So that's why we developed this system, and to summarize it, it's interpretable, which means that if something goes wrong, we can attribute it to some failure in it. That's very difficult with neural networks. It doesn't need nearly as many labels as doing a neural network like end-to-end. It needs some labels, but not a lot. Another thing, it's modular, which means that you have all these different components in there, but you can switch them out for other components. So we have a Markov model. Maybe you want to use a neural network because it performs better. Then we can just switch it out easily and leave the rest of the pipeline intact. And last but not least, probably the most important thing, because we're working with data that's on the order of petabytes, we really need to be fast. And this is very fast. Okay, now we have developed our lane change detector, and it's ready for integration into the whole processing pipeline. We take our raw data, we feed it through the data processing, and now this data processing, using our algorithm, will add the information about whether there's a lane change in there or not. This is put into a database that the engineers developing autonomous vehicles can then use. So now they can just search for, okay, I want a scenario where there's a lane change happening, and they will get the data quite easily. So to summarize and answer the question I posed in the beginning, I recorded 10,000 hours of driving data. Now what? The solution is to feed it all through a data processing pipeline that puts an extra layer of interpretable data for humans on top of it, such that the engineers that need to develop things with this data can find the right data that they want. They can discard data that is not interesting. They can delete it. And they can hopefully bring us autonomous vehicle a little bit sooner than if humans were doing all the work. So thank you for your attention. If you want to connect with me, please send me an email, grab me in the hallways, or find me on LinkedIn. Thank you very much.